And then this program is brought to you by Southern California Edison. Thank you, David Intner. I know that you are here today as well. The presenter, Gary Klein. Let me move some things out of the way here. President of Gary Klein and Associates has been intimately involved in energy efficiency and renewable energy since 1974. Mr. Klein has a passion for hot water, getting into it, getting out of it, and efficiently delivering it to meet customers' needs. He works to simplify building codes and to get architects and builders to use plumbing systems that, by their design, deliver hot water quickly and with minimal waste. After serving 19 years with the California Energy Commission, he has provided consulting on sustainability since 2008. Mr. Klein received a BA from Cornell University in 1975 with an independent major in technology and society with an emphasis on energy conservation and renewable energy. All right, I will go ahead and turn it over to you and you can start today's program.
Okay. So we're going to cover 4 topics today. We're going to differentiate conditions that existed for the default water supply calculation method from new ones that we can use using the water demand calculator when we select a method for sizing for peak water demand. We're going to discuss the savings in cost, water, energy, and carbon, et cetera, when using the water demand calculator. We're going to summarize the public benefits that we get for public health and safety, as well as water quality benefits. And then we're going to locate instructional resources for you to use on future projects.
Okay. All right, so we're going to cover these topics with particular attention being paid to one exemplary project. We're going to cover the overview and problems with the existing methods in the Hunter's curve. We're going to look at the water demand calculator. We're going to talk about the benefits, and we're going to talk about codes and standards and future collaboration opportunities. This is an affordable housing project in Oregon. It's called Nueva Esperanza, and it achieves significant cost savings by applying the water demand calculator when right-sizing the meter and the water pipes, particularly the mains between the buildings. It's a garden apartment complex. So there were system development charges, as we're all familiar with here. They have similar ones in Oregon. And they were told they were going to need to use a 4-inch water meter based on normal calculations for the sizing of the water demand in the building. So about $480,000. They came back with a 2-inch meter size and a 2-inch pipe. So their system development charges went down by $400,000 just by virtue of using the water demand calculator to give a better estimate of peak flow and therefore pipe size. That's a savings of $2,600 per apartment unit. I'd say that helps make affordable housing more affordable. What about you? It's a pretty big deal. This is a huge one. We haven't even got to the piping in the buildings. This is just at the system development charge level. So let's talk about the problems, the overview. Sizing plumbing is undergoing a major transformation. I've been working on this topic for almost 10 years now as part of my work with the Water Efficiency Standard Task Group that's formed by IAPMO. And about a decade ago, no, 15 years ago now, we received a proposal to say we ought to bring the sizing of water piping into the modern era. It's been developed, the methods we use were written down in 1940 by a fellow named Roy Hunter. Some of you may know that name. He used to work with the National Bureau of Standards, which we now call NIST. And the method of sizing has not been fundamentally changed since 1940 when he published it, even though if you read his documents, he said, we really need to fix this as we get more information moving forward. Well, in the 1990s, the federal government changed fixture flow rates for faucets and showers and toilets and urinals, and nothing flushes or flows at the rates it did back in 1940, nor are our patterns of use the same. And if you read the 4th bullet, the flow rates from the 1940s assume that every home operates like a sports stadium at halftime with people waiting in line to use the toilets and the sinks. And I'm going to suggest that doesn't happen very often anymore. And so we have lower flow rates and different patterns of use. We really ought to start looking at right-sizing the plumbing based on modern information. So reducing the volume of the water in the building's piping has many benefits. You can think of several. There's water savings potential, particularly on the hot side. There's energy saving because you don't waste as much water waiting for hot water to arrive or when the pipes cool down. You get carbon savings in first costs and operational costs, and you get cost savings in first and operational costs too. All of these sound like a pretty good deal from a construction point of view. So the key to remember is that volume is a combination of distance and diameter. Architects are responsible for the distance between the mechanical room and the wet rooms. The plumbing professionals have no choice but to connect the things so they don't leak. The closer we can put things together and better stacking and back-to-backing reduces the volume of water reduces the number of feet of pipe, which reduces the volume of the pipe. Reducing the volume is where all the benefits come from. So how can we reduce the diameter and still provide a margin of safety? Because we really don't know exactly how much water gets used, hot or cold, in a building in any given minute of time. This is an overview of water use over time, showing that from 1980 to 2030, there's a 50 to 75% reduction in water use for the typical residential fixtures or appliances that we see in our buildings. And the probability of simultaneous use is much, much less than we would estimate. So I'm going to ask a question that I'd like you to answer in the chat if you can. Imagine you have a hotel with 100 rooms in it. How many showers do you think are on at the same time on their peakiest day of their year? That means every room is fully occupied. I see an answer of 12. Anybody else want to guess? I see 50. I see 40. You're allowed I see 80. Cool. All over the map. So it turns out from measured data, it's between 10 and 15 showers are on at the same time on the busiest hour of the busiest day of their year. That's 2 hotels for almost 2 years worth of data. It's not an infinite number, but boy, it's a big data set. The plumbing code assumes 80%. It doesn't happen. There's no evidence that that happens in most cases. We can create a few cases like stadiums and flushing at halftime. That's a different case, but it is not the normal case for most buildings. Let's look at the water demand calculator. This is a screenshot showing you what the calculator looks like. It's a downloadable spreadsheet that you can bring onto your computer or even one for your phone. And it allows you on the computer to choose whether you're a single family residence or a multifamily building. And if you're multifamily, you get to pick how many apartments are in the analysis based on how many are in the building. And so this is showing you an example of running, it looks like a 40-unit building. I can't read the small print here, but and it's showing what the main line would be for the whole building. And it comes up with, what is it, about 15, 18 gallons per minute? Something like that. I know what it's supposed to say. Sorry, 26 gallons a minute. The other thing to note is that the probability of zero demand is only 1%. It means that it thinks there's going to be more than one fixture on most of the time. And in fact, that rarely actually happens at 2 a.m. There's a lot of hours of the day where very little, if anything, is happening. But because it's a big-ish building, the potential is there for simultaneity. And what's also telling us under the Hunter number is that only about 4 fixtures are on during the peak period that it's finding at 99th percentile peak. That's not very many out of how many total for the building? Almost 400 fixtures. 1% of the fixtures are on and at the time of the peak. That's not very many. It's a very small percentage. This is showing you 2 graphs, one a subset of the first. The standard method in our code is based on converting water supply fixture units, which are on the x-axis, to gallons per minute on the y-axis, and they follow that red line. That comes from the Uniform Plumbing Code. It's the same as in California's plumbing code. And it shows that that's the conversion line. Notice the little black dots crawling along the x-axis. Those are 20 different apartment buildings that are from all over the country, ranging in size from 8 to 384 apartments, and none of the black dots are close to the red line. If you look in the bottom half of this image, you'll see the letters inside the dots, and you're actually able to read the letters, and you're still not very close to the red line, which is the conversion line. It's showing us that the code is overestimating the peak design flow rate by 5 to 27 times. That's huge. If anyone does structural engineering, an oversizing of 100% is a big number. That's 2 to 1 for structural engineering. And the code is oversizing its demand estimates by 10 to 1. It's why? It makes no sense. All right. So this is looking a little bit more closely at specific buildings. The black dots are the same black dots we just saw. The red crosses, the lollipops, are what the water supply fixture unit method using our current code would give us. And if you look on the far right, there are 4 numbers that go with arrows. They're too far off the chart. We just decided to tell you how big they are. The blue lollipops, the blue crosses, are showing you the water demand calculator estimates for the peak. And with the exception of the last one on the right, they're 2 to 4 times the estimate of measured peak, the actual measured peak flow rates in these 22 buildings. It still provides a good margin of safety, and it's a much tighter approximation of what's actually happening in our buildings. This is the metadata, these 2 slides, this one and the next one, showing you how we monitored the buildings, what the monitoring periods were, the logging intervals, the times at 0 flow, and the peak gallons per minute that we actually measured. And then the California Plumbing Code Appendix M and California Plumbing Code Appendix A. Appendix M is the water demand calculator, Appendix A is the base code, and you can see the multipliers and values. This is showing you the occupancy type and the number of apartments and what was in the calculations that we used for all of this work. Just in case you're going to ask, I work in the energy space mostly. And so when we wanted to find data about water use in buildings, I called my friends in the energy space and said, well, I can get you hot water numbers. So all of the data you're seeing here is about hot water use in these apartment buildings. When you add on toilets and mixed flows for other things, nothing changes. We've got enough buildings to show pretty clear evidence that the patterns remain the same. The total for the whole building is a bit bigger than it is for hot water, but it's not double, it's 10, 15% more. It's not a big deal. Take a picture of the QR code. It will get you a link to the report that we used to get this code change proposal approved for California. We were successful in the interim cycle, and it shows what we've done to do the work that I've just described. Let's talk about the benefits. You can keep clicking. So there's construction cost savings. There's ongoing cost savings. There's faster delivery of hot water to occupants. There's embedded water and energy savings. There's additional energy savings due to heat loss in the hot water distribution system. Reduce carbon emissions for embodied and operational. And by reducing the volume of water in the building, you have shorter dwell times. And that's a huge win for pathogen management in our plumbing systems. So this is showing you an example of the benefits of right sizing. This is taking a 6-unit apartment complex, and we're looking at tables 6 sizing on the left, Appendix A sizing in the middle, and Appendix A with the water demand calculator on the right. Same layout. All we're doing is changing the diameters of the pipes. So pipe 1 is at the service entrance at the beginning on the far right of the diagram, blue line. The code says to estimate a total of 1.5 inches for the pipe, and 38 gallons a minute. If you read the middle, it's the same information. The water demand calculator for the same building expects the peak flow to be only 13 gallons a minute and only a need for a 1-inch pipe. That's 2 pipe size reductions. You can follow the logic for the other parts of the plumbing. In, I think, all but one case, the diameter goes down by at least 1 pipe size. That's a big deal. It turns out in approximate terms, if you can reduce the diameter of the pipe 1 size in the building, you cut the water volume in the building roughly in half. That means for the same use, your turnover is twice as fast. Turnover twice as fast means that you're bringing in new water from the municipality, which has been protected with some form of disinfectants, and that means you're turning over the disinfectant into the building more quickly for any given use rate. That's what's protecting health and safety. And if you ever have to flush the lines because of other concerns, you have half as much water to flush in order to clear the line out and make it safe again. So we've done some estimates of cost savings. I've worked on some projects where I have some real numbers. And I'm happy to discuss them. But this is an estimate from 2022. We haven't updated it. The savings are just bigger because costs are higher. We found $600 to $1,200 per dwelling unit of reduction in first costs by virtue of using the water demand calculator. And a bunch of that's dependent on the water connection fee. This was in Seattle. Depends which part of town you built in, how much you get to save. That's a big difference per apartment unit. As we talked for Nueces Esperanza at the beginning, their system development charges went down $400,000. That doesn't include the savings in pipe fittings and water heaters that you get to account for inside the buildings. So it's a big deal. It's really worth working on. So we have found from our research that water and energy savings range from 200 to 1,600 gallons per dwelling unit for the buildings we considered. I'll come back to these in just a second. Natural gas savings raised from 3 to 8 therms per dwelling unit for, again, different building types that we looked at. And the water and energy savings turn out to be highly dependent on the plumbing configuration and the fixture use patterns. So I'll give you a couple of examples. Do you know anyone who waits a long time to get hot water somewhere in their house after they turn on a tap? You can raise your virtual hands. I'm pretty sure lots of us. Does anybody wait at least 15 seconds to get hot water somewhere in their house? Yeah, lots of people. Okay. Does anybody wait 30 seconds or more? How about a minute or more? Do you realize the American Society of Plumbing Engineers says 10 seconds is all you should wait? And most of us wait much longer than that. Well, I'm going to give you a clue. Part of the wait is architectural decisions, and part of the wait is the diameter of the pipe. I believe I'm talking with the architects today, so I want to pay a bit of attention to architectural compactness. We don't have any slides particularly on this question, but it's really important. It seems to me that many buildings, particularly single-family detached stuff, the water heater is located in a garage. We live in California. We don't get basements. And if we're lucky, that water heater is next to the wall of the house. Okay, not at the front of the garage where the door is. So if it's located there, I'm willing to take a pretty good guess that either the primary bathroom or the kitchen is diagonally opposite the water heater somewhere on that floor plan. I don't care if it's 1 story or 2, but I see an awful lot of floor plans that look like that. That distance has to be overcome every time you turn on the tap at that location to get hot water to that location. And in general terms, that first pipe is almost always 3/4 inch pipe. Sometimes it's bigger, but for single family residential, it tends to be about 3/4 inch pipe. 50 feet of 3/4 inch pipe PEX is a gallon, 40 feet in copper. That distance across a 1,200 square foot house is 80 feet of pipe. That's 2 gallons, 1.5 to 2 gallons. You have to clear that volume out before hot water gets there, and then you have to wait for the hot water to get hot. The reason right sizing has such a big win is we get to reduce the diameter by 1 pipe size in general. That's what happens. And that cuts the waste and weight in half. And when you're done with the event, you have half as much water in the pipe to cool off. So you get a water savings and an energy savings every time you use hot water if you've right-sized the plumbing. I see a hand up from David. Do you have a specific question, David?
No, I just was trying to figure out how to raise my hand when you were asking about how long I wait for my hot water.
Got it. You can put your hand down then if you get lucky. I'll ignore it for the moment.
I'll
Thank
see
you.
if I can
Next.
figure it out.
Yeah. There you go. Reactions. Go to reactions or more or something. There you go. The other thing on the last bullet here, I talked about the plumbing configuration, but I didn't talk about the use patterns. I'm a morning shower person. I typically don't shower until after the alarm goes off. And so I get up in the morning, I go to the toilet, and then I go to the shower. If I turn on the shower before I get into the toilet, it takes, in our case, 30 seconds for hot water to arrive. Okay. If I waited, I'd have to wait 30 seconds after. But if I chose to use my sink first, I'd prime the line to the sink before the shower. If I went to the kitchen first instead of the bathroom first to make coffee, then I would be priming different parts of the plumbing system. Patterns of use determine waste and weight as well. We can't control patterns of use in our buildings. We, as architects and as engineers, have control over the infrastructure we put into the buildings. We need to make that as efficient as possible, given any pattern of use. So this is looking at how we got to our savings estimates. I don't think I want to spend a lot of time reviewing it here today, but we can go into detail if you'd like. We have single-family dwelling units, and I see a small typo in single family. We want to fix that, Carrie. The other estimates for multifamily buildings, we looked at a bunch of different prototypes and did the analysis. It varies a lot depending upon the configuration of the plumbing and which fixture is at the far end of the system. Sinks get used much more often each day than showers do. And so every time the sink cools off, it's going to cool off to the branch of the sink is going to cool off at least once every hour. Same for the showers, it cools off within an hour after you're done. And so the patterns of use matter and how much savings you can estimate matter. We only counted kitchen sinks and showers for the water saving estimates. I don't know about you, a whole bunch of the time when I need to rinse my hands or wash a peach, I just use whatever temperature comes out of the faucet because I'm not looking for hot water hot enough to shower in or wash dishes in. I'm looking for some water to make a rinse. So we only counted 2 key fixtures in our estimates. There are carbon savings. IAPMO has done a report. Arup was the engineering firm that did the work. And it shows that you get to save a bunch of carbon embodied in terms of the way the building is built. What they also found in the second bullet is that booster pump savings in the high-rise buildings are huge, 73 to 84%, because you're not trying to boost as much water up to the top of the building. You still have to overcome the vertical height of pressure, but you don't have to move as much water to do it. It's a big deal. Here's some resources on the benefits. There are several reports. They're all publicly available. The links are here in the chat. Sorry, down in the chat at the bottom of the presentation. And I highly recommend if you want to learn more, you should go read all about them. There's a lot here to deal with. And that QR code would be really helpful. I would take a picture of that and use it. It gets to IAPMO's webpage on the water demand calculator resources, and it will get you to lots and lots of information to help support your understanding of this. All right, let's talk about the water demand calculator in the codes and standards. The blue items on the map are where the water demand calculator has been adopted, mostly in uniform plumbing code states because that's who they adopt the uniform plumbing code. The water demand calculator is Appendix M in the uniform plumbing code, but it's also referenced in the ASPE documents and the WESTAN documents. And I know that there is a dot or two in Colorado because some of the jurisdictions there, they're a home rule state, so each city gets to pick its own codes, have already adopted the water demand calculator into their plumbing codes. And if you look carefully, it's mandated by the state energy code in Seattle, by the city energy code in Seattle for all R2 occupancies. You have to use the water demand calculator in order to comply with the energy portion of the code. So it's been pretty widely adopted. I will tell you that the first 2 states it was used in were Texas and New York, both of which are not uniform plumbing code states or international plumbing code states. The project in Texas was done in 2016 and 17 while we were developing the final version of the calculator. We were able to actually right-size the piping in the homes and in the street. So that's a big win for the construction costs for the project. And in upstate New York, I worked on the second phase of a two-phase garden apartment complex. Phase one had 3-inch pipe going into each of the 35-unit apartment buildings. Phase two had 1.25-inch pipe going in based on our review of the water demand calculator, and saved in first cost over $800 per apartment. And we were already in the middle of negotiations because they'd bid phase two as part of phase one. And as you know, the owner never wins when you have to renegotiate price in the middle. And they still got $850 back per apartment in first costs. It was a huge win in piping. This is what's true in California. It became effective July 1st of last year based on our efforts to amend the code in the state. It applies to new residential construction, meaning single and multifamily buildings that look like apartment buildings. So even dormitories that look like apartments, it's applicable to. And you can use it now for renovation or adaptive reuse projects. One of the big wins is that if you don't have to change the pipe if you want to convert an office building that's got a 3-inch pipe coming into it because it's an office building, and you want to convert that to apartments, you might not have to change that pipe or the meter size. You can live with what's there. You probably go to a smaller meter, but you wouldn't need to replace the pipe from this municipality into the building, which is a very expensive proposition. And you'd be able to use the right sizing inside the building to get the right dimensions for all the water use fixtures in the building. So chapter 6 on the far left points now to Appendix M. It didn't used to. Appendix A, which is below on the left column, tells you there's an exception for applicable fixtures. You may use Appendix M values, and Appendix M values are shown in the right-hand column of this sheet here. They are adjusted for California because California has its own rules for water use efficiency. For mostly the ones that matter here are lavatory faucets, shower heads, and kitchen faucets. Everything else remains the same as the maximum flow rates. This is what's in the 2025 California Energy Code. This will take effect in January. It is part of the prescriptive requirement, so it's sort of the base by which calculations will be compared. And hot water piping shall be sized in accordance with California Plumbing Code Appendix M. It doesn't say you have to use it in the building, but it's the basis of comparison for the energy designs that you're putting forward. Here's the excerpt from the Seattle Commercial Energy Code, and it explains where it can be used, and it took effect in November last year. I'll let you read it for a minute. If you look at it carefully, it sort of says in the second sentence, piping shall be no more than one pipe size larger than the minimum size permitted when used for the maximum allowable velocity based on the specified plumbing materials. That's a really complicated sentence, but because it's new, it's really hard for everybody in our industry to understand that the hydraulics will work when you have lower flow rates. So in order to appease that fear, they're saying that if the water demand calculator predicts the need for a 1.25-inch pipe when you go through the sizing methodology, you're allowed to use 1.5 inches for that pipe. By the way, it would have been 3 or 4, so it's still a big win, right? From an energy and water and materials point of view, but it makes it a little less scary. To address this question, we actually have a pressure testing lab in Madison, Wisconsin, that was able to we were able to run a project from Portland, Oregon for a 10-story apartment building where we actually built the plumbing from the service entrance all the way to the furthest fixture on the top floor of hydraulically most remote fixture, an apartment. And we ran it at the water demand calculator predictions in order to see what the pressure loss would be in each of the segments of pipe. And what we found is that even at the water demand calculator predictions of over 28 gallons a minute for that apartment building, the maximum velocity in the 1.25-inch pipe never exceeded 3.5 feet per second. The plumbing engineers design that pipe for 8 feet per second, and they're not getting even half of that. That pipe could have been 1 inch in diameter from a hydraulics point of view. But because the building was so tall, they decided not to go down to the next size smaller because they're worried about making sure there's enough residual pressure on the top floor. It's a balancing act. Architects are responsible for the distance. Plumbing engineers are responsible for the hydraulics. We have to work together. AWWA has a new sizing document that came out in 2024. It's the 4th edition of their water meter sizing and service line manual. It now recommends using the water demand calculator for estimating the peak flow rates in residential buildings. It's taken a while to get there, but this is the current document that all water management systems around the country are going to be using going forward. And for residential applications, we should be using right sizing in accordance with the water demand calculator. The water demand calculator doesn't size the pipe. It does a better estimate of peak flow rate for the key fixtures in question. Methodology in the code is still followed by the engineers to size the pipe, but instead of 3 and 4 inch pipe, we're ending up with 1 1/4 to 2 inch pipe for the main service entrance for an awful lot of buildings. That's a big, big change. Collaboration opportunities moving forward. I suspect that many of you work on projects that are not residential. Long-term care, commercial, hospitality, dormitories, hotels, you name it, lots of things that are not strictly residential. IAPMO is now working on a version of the calculator for each of these other occupancy types. To the extent you have access to buildings and can help us get data from buildings at the flow meter data stuff that we talked about earlier, we will be able to incorporate that information into a commercial version of the calculator to cover initially all other occupancies than residential, but eventually specific to each occupancy type. I can make a pretty good case that long-term care in healthcare is different than hospitals or urgent care because there's different things in the building. So we ultimately want to have a calculator that's tuned to each of the building types we have. So we need your help to get there. The sooner we get to the number of buildings we need, the sooner we'll have the calculator ready. This is the specifications for the needed data. We need 3 to 4 weeks of monitoring. We want to have no more than 60-second time intervals for the data acquisition. IAPMO is willing to help you get access to meters. If you've got tall buildings, one of the best things we can do is to put a meter on the booster pumps, because the booster pumps are telling us what's going on for pretty much the whole building every minute of the day. We just need to track the data at finer time intervals. And it turns out we don't need that many buildings, but we need 140 or so of each type in order to make a tuned calculator. We're getting there, but we need your help to get there quicker. So what can you do? Well, let's see about using it on your next projects. You need to opt in, so you have to ask for alternate methods and means. I would be happy to continue this kind of conversation in small groups with you and your teams of projects so that you can learn specifically for each project what to do. You should share this presentation with your teams, go over it, have a lunch and learn. You can invite me to listen in. Those are the sorts of things we need to do to get projects moving forward all over the state. And some of you are going to tell me about problems you have dealing with the city of LA, and we'll cover those in Q&A. This is all viable throughout the state. So then you have to ask your plumbing engineers to attend future trainings, because all we've done today is give you an overview. IAPMO's got lots of resources on their website. They're willing to help to apply to specific projects, as am I. And we just need to start sharing it around and move forward. I would be looking at your projects that are 6 months or a year out. The ones that are already in the books for next Tuesday are a little late for this. But if you've got a willing client, happy to help you figure out how to do it. So, all right, I think we should open it up for Q&A.
Gary, I'm not seeing anything in chat right at the moment. Would you like folks to unmute themselves, raise their hand,
Yes.
put it in chat?
Yeah.
Okay.
Yeah, raise your hands. Let's just make this an open mic. I know you have questions. I can't believe I answered them all in my presentation. By the way, you've got to go 7 more minutes in order to get credit anyway, so somebody ought to ask a question.
You made no mention of research.
I
If
did
you
not
read
mention research.
Your hot
Um,
water source has a shorter distance to the fixture.
So Frank, your question is
So
about
there's a little more
recirculation.
expense in yes.
All right. So Frank, if I understand correctly, you said I didn't mention recirculation. You are correct. I did not. So recirculation comes in 2 forms. There's the supply portion, which the water demand calculator will help with the right sizing of, and there's the return portion, which it is not intended to apply to. So the thing about recirculation is it's basically moving the water heater from the mech room closer to the apartments in an apartment building or the fixtures in a single family detached. And so there are energy costs for running recirc loops. And that's an entire presentation I have that's not on today's discussion about whether you've got single zone or multi-zone recirculation systems. I work on committees on both of those things nationally. Happy to have another conversation with the AIA group here to go over those different strategies for proper recirculation. But the key is that if you've got the water close, that becomes the new water heater, if you will. So if we put a water heater in a building or an apartment, or we put a recirc loop with a branch to the apartment, that point of connection becomes the new source of hot water. And so there's a loop question separate from the use questions inside the dwelling units. And both are needed to be considered. The water demand calculator covers the supply portion of this. All right. I see Zarin's hand up. Or Barham's hand up. I can't tell.
Hello, that's me. Thank you very much. Thanks for the presentation. I have a question in regards to residential. If you have a sprinkler system, how does that kind of tie into your design and calculations, or if it does at all?
So, if we're in single family residential, there's a lot of combined systems where you're using the cold water supply as the source for both cold water use and for the sprinkler heads. Those systems tend to get sized for the sprinklers, not for the use. But what I would observe is there is no need to add the two together to size the cold water piping. If you have a fire in your house, you want to know to get out of the shower because there's a fire. Okay. I don't think you have to size additively. I think you only have to size for the big use. If we're in an apartment building, the fire system is separate from the water supply system. And so that would come in either on the main branch and be split off at the beginning of the building. It might have its own complete separate branch from the municipality. It sort of depends what your jurisdiction does. But from the moment of the split, the water demand calculator will take over the sizing of the uses in the building.
Thank you.
All right. So I'm looking at the chat.
Yeah, we do have questions in chat now.
All right. So let's go through them one at a time.
You want me to read them off for you?
Well, I can see them, but go ahead and read them out. It's fine.
Okay. The first one was at 12:45 from Alex. Are there any opportunities for reductions in DWV piping that would parallel the supply piping size reductions?
Not yet. It turns out that there's an effort that's being sponsored by the International Code Council, Standard 815, which is looking at the right sizing of water supply and drain, waste, and vent. I'll give you a clue. From our research so far, there is virtually no need to have a bigger pipe in the basement of a building with lots of vertical drain pipes than a 4-inch main. The lack of simultaneity is so big that 4 inches covers about 99% of all cases we've evaluated so far. And I know our plumbing code says, well, you got to go to 8s and 10s and 6s and all that stuff. Our math is confused because the lack of simultaneity is not properly accounted for. We don't yet have we don't yet have a firm method yet. It's coming. Next one.
Okay. This is a question. Some time ago, I asked a plumber about converting to InstaHot, but he stated that my home had 1/2-inch piping and needed a minimum of 3/4 inch for InstaHot.
Well, InstaHot's a funny question. I'm guessing we mean tankless of some form. InstaHot to me usually means the thing next to my kitchen sink to make boiling water, in which case I could use 3/8 tubing. If we're doing about on demand to run a whole building, you pretty much need to have, depending on the size of the burner or the electric elements, you can use 1/2 or 3/4 inch pipe. Andrew, I'd be happy to chat with you more offline about this, but in general, the plumber is being confused. The bigger issue is really how are you going to get power or gas to the site where you need to run the InstaHot. If you only have 120 volts, you can't get a very big heat rate. It's a problem. All right, enough for now. So then I see Philip.
Yes. Are you talking to the local universities to get existing building data?
We have started communications with the UCs and CSUs, but any of you who are working with them could ask the question again. They want to be helpful, but they need projects to look at. So if you're doing project with the UC system, I would say, or the CSU system, it's say, let's get a meter on some of the buildings that are similar to the ones we're designing for you so we can tune the plumbing for you and save you some money. And projects take more than a week to design, right? So put it in now, a month later, we'll have data and that'll help true up the building. I think everyone would be appreciative and it's one way to get more data.
Next question. If we are using a lower volume meter and a reduced sized piping, are we limiting ourselves to future expansion or additions of fixtures in the future?
So most meters don't read well at normal flow rates. Revenue meters are sloppy because of grit in the water. So they don't read flow rates below a gallon a minute very well, and the bigger they are, the worse they read them. Yet most of our flow rates in most buildings are under a gallon a minute. That's the most common flow. So we have a double-edged sword. We think that if you can use a 2-inch meter, now you could still use a 2-inch meter when your flow rates go up to 50 gallons a minute. It's not a problem. If you start with a 4-inch meter, you're missing 2/3 of all your flow rates. So it seems to me we have to right-size the meters anyway in order to properly read what's going on. Then the other part of the question you asked is, are we limiting to future expansion? The water demand calculator estimates are typically 2 to 4 times bigger than what we see as peak flows. How much expansion are you planning to add? Are we going to add a whole new building? In which case, we're probably going to end up with a new meter. In which case, I don't have to make the first one bigger. If we're going to extend a building, we need to think about that expansion potential now. But in practice, we rarely see the flow rates going up double when you double the amount of fixtures. They tend to tail off. And so I don't think we're limiting ourselves much, if at all. And I think from a public health and safety point of view, we want to be very careful about oversizing for future expansion. We need to think more carefully about how to bring the new water to the new section more effectively so it doesn't impact the design of the basic build, the starting of the building. Then I see Craig's question.
Yes. Let's see. So many residential buildings in most counties don't benefit from architects and engineers. How do we get WDC design into these buildings?
It's a great question. So I'm guessing that mostly single family residential doesn't get much architecture or engineering, certainly not the production stuff. Custom homes get some architecture and engineering. Most of our work tends to be for bigger complexes, apartment buildings of, 4, 8, 10, 50, 150, 300 units, whatever it might be. So for the ones that don't get it, I think we need to have Well, in each jurisdiction, there are, I'm going to guess, chambers of commerce. There's building industry associations. There's local chapters of lots of things. There may or may not be AIA chapters in each of these communities, but we can start sharing the basics of this with the people who do normal construction, the building departments in every jurisdiction. We could create a one-page fact sheet, laminated both sides, that kind of thing, put it at the counter, let people know it's available, and refer people to a resource, either IAPMO or some other organization to help. That's what I would be doing at this time.
Okay, and then there is one final question. Is there a major perceivable difference of shower flow pressure when changing the line diameter, or does this depend on supply pressure or system assistance like recirc pump?
So I'm going to make a pitch for another presentation to give you all called Why Your Shower Feels Wimpy and What You Can Do About It. It will answer this question in depth. I'll do my best to do it in a minute here. So the answer is no, but you have to choose your shower valves and your fixture flow rates, not your flow rates. You have to pick the pressure compensating flow regulators for your faucets and shower heads. Let me describe what I mean. We've measured the pressure loss through modern pipe and fittings for 70 different combinations of 1/2 and 3/8 tubing, copper CPVC, and PEX. Common materials used in the plumbing environment in the United States. We now know the pressure loss per fitting and per foot of pipe for all of these combinations. So we can predict what the pressure loss will be on the last 20, 30 feet of pipe to any given fixture or appliance in a building. We know what it's going to be based on its starting pressure. We know the loss. The shower valves that are typically found in residential applications at California's legal shower head flow rate of 1.8 gallons a minute vary in pressure loss from 4 to 14 psi through the valve while operating. That's a factor of 3 difference between choice 1 and choice 2. Well, if you started with 50 and you lose 14, that's a big loss on the way to your shower. If you start at 80 and you lose 14, yeah, it's a big loss, but it's not as significant. Shower head flow rates are rated. The ones you buy, if you buy a 1.8 gallon per minute flow rate, it's rated at 80 psi. The plumbing code doesn't allow us to put 80 psi to any fixture in the building. So you'll never get the rated flow rate. The people who make the inserts that go into our faucets and shower heads, a company called Neoperl, Neoperl. They're like the Intel inside. They make almost every type for almost every brand sold in the US and Europe. And so we're likely to see their inserts. They come in 3 categories. One is a fixed orifice, which is a hole with pressure behind it. And if you have a pressure problem, you will notice it if you have a fixed orifice flow regulator. Because as the pressure goes down, the flow rate goes down at half the square root of 2. So 0.7 when you go from 80 down to 40, and 0.7 again when you go from 40 down to 20. Most buildings are in the 20 to 40 psi range at the shower heads. It's a pretty typical number. And if you didn't like 2 gallons a minute, you're going to hate 1 gallon a minute. And so the way you avoid that is by picking pressure independent flow regulators that Neoperl makes for shower heads and for faucet aerators. And that's the way to solve this problem so you don't notice it. The recirc pump, by the way, does not boost pressure. All it does is move water around. It's not a pressurizing pump, it's a circulating pump. So we have to follow the logic once we're on the branch to the showers. And what I've just explained takes about 45 minutes. It'd be a great another presentation for you to do so you can learn all of the physics behind it. It's a lot of fun. All right. I think we're almost ready to wrap up.
Yes, there's no other questions.
Well, I think we did pretty good then.
Yeah.
Thank you all for your time and your questions. I hope it was helpful.